This is lecture 2, part 3 for systems thinking tools. And this is part of the material cover for the Introduction to Systems Engineering course and the System Thinking and Analysis course. As always, we start our lecture with the references that were used in the preparation of the material. So in this case, we used textbook by Hitkins, Advanced System Thinking, Engineering and Management. So in this lecture, we are continuing our discussion on system thinking topics. And in this lecture, we're going to focus on some diagrams that are useful in developing these ideas. Diagrams that can allow you to see the problem from different perspectives and can allow you to understand the problem better. So there are two types of diagrams that we are going to discuss in this lecture. The first one is called the causal loop or the influence modeling diagram. And the second diagram is the n-squared charts. In this first part of this lecture, we're going to focus on the causal loop models. So at the end of this lecture, we're going to have an activity in which you're going to prepare a causal loop model for a specific situation that I'm going to explain. And then on our next lecture, we're going to discuss the n-squared charts. But for this lecture, our focus is on the causal loop. So before we get into the material, I like to bring these quotes from different people that are quite famous. So in this one, we have, how can I tell what I think until I see what I say? So the idea behind this quote is that we have to really have a good understanding of what we want to explain before we say something. So from a system thinking point or from systems engineering viewpoint, what this means is very important for us to have a good understanding of the problem. And the tools that we are going to discuss in this lecture are good tools for those purposes, understanding very well the problem. So system thinking tools, as I mentioned already, causal loop diagrams are a useful way to represent dynamic interrelationships. They provide a visual representation with which to communicate that understanding. So again, we want to be able to represent the dynamics of a specific situation. And this causal loop is going to provide a visual representation for those purposes, so you can communicate the understanding of the situation. What are the components of causal loop diagrams? We have variables. These are an element in a situation which may act or be acted upon. These vary up or down over time. It's not an event. And we use, in order to represent them, we use nouns or noun phrases, not action words. And in addition to the variables, we have links or arrows, and these are used to show the relationship and the direction of influence between the variables. So there are many ways to look at the world. Causal loop models allow for modeling nonlinear systems using cause and effect. So some of the viewpoints or different ways of looking at the world includes the disjoint. So meaning that we have cause and effect of separate situations, and these separate situations that they don't interact with each other. So that's what we are presenting here at the top, the disjoint point of view or viewpoint. We had the linear or control viewpoint, in which we have this linear connection between cause and effect. So this event causes or has an effect on the next event, and then this one has an effect on the next one, and that continues. But there's no feedback, right? In this linear viewpoint, you have a start point and you have an end point. And then the third viewpoint is the nonlinear feedback or causal loop, in which an event can create another event and then another event, and that event can have an impact on that first event that originated the actions. So these sign digraphs, joint rates, and levels of relevant factors. They represent the flow of causality. As a note, always state your notation when constructing a causal loop model, because you want to represent the viewpoint, right? You want to see if there's a positive reinforcement or a negative reinforcement between these variables. So what is the disjoint view? The disjoint viewpoint of discrete cause and effect is the antithesis of system thinking. Okay, so we talk about the disjoint point of view or viewpoint. That's this part right here, in which we have this separate cause and effect, and there's no interaction. The disjoint viewpoint looks for a singular solution or a silver bullet. For the linear control view, many engineers, planners, project managers take a linear control viewpoint of cause and effect. They string activities into sequences. The output or the effect of one becomes the input or the cause of the next event. And some examples that you might be familiar with are Gantt charts or PERT charts. The linear control viewpoint is dominant. This is pretty popular, but it's deeply flawed since it does not take into account reaction. Stimulating any system causes a reaction, which opposes this stimulus. The reaction is at the heart of science and engineering, yet it is often overlooked when developing plans. Okay, so this is the continuing triumph of hope over experience. And last one is the nonlinear feedback. And the causal loop nonlinear feedback viewpoint comes close to the real world. And that's what we are trying to use here in our modeling of systems. Cause results in effect, which feedbacks sometimes through other systems to interact with the cause. A causal loop is generally either negative or positive in the sense that feedback or the effect either counters or reinforces the initiating cause. So let's discuss some examples. What I'm going to do now is I'm going to try to draw some causal loop models for two problems. The first one is called the population dynamics. So what I'm going to do, I'm going to state the variables for this problem. So typically In this problem, we have 3 variables, which is the population, and then death, and we have births. And those are my variables. And if you see here at the bottom of the slide, we have a notation. So I'm defining the notation that I'm going to use for my arrows. A hollow arrowhead denotes reinforcement. A solid arrowhead denotes a contrary or opposing effect. Okay, so I'm going to start creating some arrows between these variables. And then population has a reinforces death, meaning that population going up, going down will have an impact of going up, going down in terms of deaths. But we know that deaths has a negative effect in terms of the population, meaning that deaths will decrease the number of citizens or the population in the world, for instance. When we look at the other side, more population, we expect to have, with more people, more birth. So that's a reinforcement. And with more birth, we have more population, increase in the population. So this is the causal model for the population, including birth and death. The idea now is that you can see how the population is affected by these 2 variables. More population, you expect to see more deaths. And as you see more deaths, you expect to have a contrary or opposing effect in terms of your population, or in this case, the decrease in the population. On the left side, population, you expect to see more births, more people. And more birth increases the population, so it has positive effect on the population. The second problem is called the dynamics of resistance to innovation. So this is a problem in most of companies in which you have most of the time new people coming with new ideas in terms of the new products, new research, and most of the time these innovators are faced with resistance from people in the company, maybe old timers that are used to do things in a certain way, and they oppose to changing those ways of doing things. So we are going to go through the same process. I'm going to list some variables that I believe are important for this problem of the dynamics of resistance to innovation. And in the center, I will have the main topic, which is innovation. And then some of the variables I can list: change. Key change is an effect of innovation. Another effect is resentment. Another effect could be some type of reaction, and also some type of opposition to innovation. And then this is from the negative point of view. From the positive point of view, we can think about new ideas generating new products, which can increase your sales. Sales would translate into profit. More profit, more ideas can be developed, more money can be put into research. And with new research, you expect to generate new ideas. Okay, So these are variables, and now I'm going to use the same notation to connect these variables with my main topic, which is innovation. So innovation will have a positive reinforcement. It will create change, but change also will have an increase in the resentment from the old timers, which will also have a reinforcement of reaction and reinforcement of opposition. And with an increase in opposition, that will translate into having a contrary or opposing effect into the innovation. On the other side, we know that innovation can increase your sales, new products. That will also have a positive effect on your profit, which will translate into more research and more ideas. If you think about Tesla and this Elon Musk, he has multiple businesses running at the same time, starting with PayPal. He was able to generate some with this innovation, increase the profit that translated into research in new ideas like Tesla or SpaceX. And with the development of these new ideas, you increase sales, profit, research, and then you create more ideas. But those are not coming for free, right? You have opposition, people not wanting renewable, people that are used to using gas engines, not wanting to or resisting change, and so on. So here's a comic also to illustrate this situation, Dilbert. So you have the boss here saying that our goal is to write bug-free software. So they want to write software that had no bugs. And then the idea is that the boss says that he will pay a $10 bonus for every bug you find and fix. So, so when you do that, then you might think about, is that the reaction that you expect? See on that second box, because that's the behavior that can take people can take that from a wrong perspective, or maybe understanding it correctly. The idea is not to generate more bugs and fix them and generate profit. The idea is that you limit the number of bugs that you create when you do coding. That's why at the end you have, I hope this drives the right behavior. So I'm gonna write me a new minivan this afternoon. So that's the idea. So if you don't have a good understanding of cause and effect, which is what we're trying to achieve with these tools, then you might end up creating a positive effect on the ideas that you want to generate. So in this slide, what are examples? Causal loop models, dynamic of resistance to innovation. The causal loop model shows how the overall combination of systems behave, but at the same time ignoring the organization structure of the company. So for the dynamics of resistance to innovation, the causal loop model suggests how the issue of opposition to innovation might be tackled. For example, we can reducing the effect of the right antagonistic loop will allow for innovation to flourish. One way to do that is to involve the organization in the innovation process, so they don't feel that they are getting behind, especially these old timers. So you make them part of the process and you educate them in terms of what you want to achieve with this innovation and how are they part of that new trend within the company. So here are more examples for the causal loop models. On the left, we have a causal loop model of body temperature regulation. This is more scientific type of causal loop model. And then we have another example on the right, which is called the kill inhibition in humans. And this one is more targeting the social aspect of people getting used to see murders and how some of the things that are happening within the society are contributing to this killing the inhibition in humans. So you can look at these two as additional examples. A causal loop model expresses openly and very clearly the thoughts and ideas of its originator. Causal loop models enables dialogue. These are tools that are built for brainstorming, allows for correction and further development. So we are not expecting you to get a perfect causal loop model on the first trial. So it's a process, an iterative process, and correction and further development as you discuss with other people. It is useful for representing the behavior of nonlinear dynamical systems and promotes and ensures completeness. Okay, so this is what I was mentioning at the beginning of the lecture. So now we have an in-lecture activity, so you should use the rest of the schedule lecture time to work on this activity. So essentially what you're gonna do is you're gonna create a causal loop model. And we are gonna use a situation that I assume most of you will be familiar with, which is staying at a hotel. Okay, so what you're gonna do is you're gonna list some good factors and bad factors of your experience staying at a hotel. And you're going to use those two lists, good factors and bad factors, and you are going to use negative inversion to construct your causal loop model. So you're going to create a list of negative factors and deliberately consisting of a pejorative adjective and a noun. And then put the various factors together and drop the pejorative term. So for example, a low cost efficiency, you can just say efficiency. Dirty, laundry, you can just say laundry. Badly cooked food, and sloppy service, you can say just service. So you're gonna use that list to build this causal loop model. So now using the information below and 3 of your adverse comments, construct an ideal world causal loop model for the hotel. You're going to connect the factors in your causal loop model as indicated by the dotted lines on the causal loop model on the next page. And you're going to assume that the business revenue reinforces cost efficiency, which is the extent to which hotel resources are converted into improved service quality and customer satisfaction at a minimal cost. We are talking about these 2 boxes here. So you're gonna put 3 of those items that you included in your list. You're gonna put one here, one here, one here, and then using these dotted lines, you're gonna create the lines, the reinforcement or negative reinforcement between the thing that you listed and the other parts of the causal loop model, which I'm providing. Okay. And at the end, I want you to answer this question. So after you generate your causal loop model, you can answer this question. What's those your causal loop model suggests about improving service quality? So I can tell you there's no right or wrong answer for this exercise. I want you to think about it. I want you to connect this. I mean, you're gonna use every dotted line. Just have to, so if you think that laundry increases or have a positive reinforcement on service quality, then you can just say, right, or draw something like this. Okay, so you're gonna do that for every dotted line in the diagram. And then at the end, once you have the whole thing, you're gonna answer this question. What does your causal loop model suggest about improving service quality? Okay, so that's gonna be your lab for this lecture. So you're gonna see these forms in the modules. And then we're gonna stop here and we'll continue on our next lecture. Thank you.